Hello, and welcome to a digital statistics lecture for Salt Lake Community College. In this video, we're going to be going through section 6.2, the Binomial Probability Distribution. We are going to have one list that I would like you to pre-make, and if you see I already have it here in list 1, it's just the numbers 0 through 5. That's all I need. It's technically a few pages from now, but that's the only list that I will ask you to have pre-made in your calculator at the moment. I'll keep it up for a little while before we get into some calculations. So here, what we are going to do is how to find the probability of a specifically discrete distribution when there's only a binomial number of outcomes. We've done a couple of these before in the past. If you remember the sauerkraut problem, where we dealt with the probability of somebody liking sauerkraut and the probability of them not liking sauerkraut. We did that back in section 5.3. It'll be similar to those kinds of situations, but we're going to be able to use this to extrapolate and solve for more complicated cases that otherwise took more time. The binomial probability distribution is a discrete probability distribution that describes the probabilities for experiments with two disjoint outcomes. And it follows four specific cases, or four specific notes that we need to identify in order for something to be binomial. The first criteria is that for each trial, there are two disjoint outcomes, which we typically call a success or a failure. So success, failure, true or false, A or B, yes or no, live or die, stuff like that. These are all disjoint outcomes, which means some of the ones that we just did in the previous section at the end of 6.1, where we had individuals living or dying for insurance policy or winning or losing for a gambling game, those were both binomial distributions. Trials are independent of one another, which means that one outcome of a trial does not influence another trial, so they should be independent of each other. Sometimes this is explicitly stated in examples, sometimes this is something you need to argue or you need to assume. This is one of the harder ones to verify, and sometimes we even let it go and say, hopefully it's independent. For the third one, experiment is performed a fixed number of times. Each repetition of the experiment is a trial. What this means is that at the beginning of the experiment, you explicitly outline how many times you are going to do something. So like flipping a coin, which is binomial. I'm going to say that I will flip a coin 10 times and see how many of those 10 times are heads. That would be a binomial experiment. I am saying at the beginning that I'm going to flip it 10 times. I'm not doing something arbitrary like I will flip this coin until I get a head. That is something arbitrary where you do not know how many trials there will be. So you needn't have a fixed number of trials, which we usually say is n. And lastly, the probability of success is going to be the same for each trial. This kind of ties into the independent situation, but for any other reason, the probability of success should not change, or there shouldn't be any indication that it does. These four criteria can be summed down into a nice acronym that a lot of people use for binomial, which is BINS. B-I-N-S. B standing for binomial outcomes, which is the success or failure. So the binary outcomes. I stands for independent. N stands for the number of trials being fixed. So N is fixed. And S means the same probability. Now, when you're solving for binomial and when you're trying to argue that something is a binomial experiment, what we do not want to see, again, what we do not want to see is you to just write down the four letters BINS and call it a day. That does not solve the problem. What you need to do is verify and argue each of these points. And you don't need to do it too in depth, but you need to at least identify them. For B, you can say that it's true or false. That's it. That satisfies the condition for binary. For I, you need to say something about independence. For N, you can point out what the number of trials is. That's enough. But you cannot just write down the word BINS and say that's enough for that problem. We have students do that too often, and I just need to highlight that. Okay. Now, there's a formula for binomial probabilities, and it's shown like here. And it looks more complicated than it really is, honestly. It's shown as NCX, which is a combination of n choose x, and then you have the probability to the x power times 1 minus probability to the n minus x power. Now again, that does look more complicated than it is, and we've actually already done this in practice. We've done a couple problems where we used this formula, but we didn't know that we did. and I'll explore that more in depth on the next page. But for now, let's point out what the variables mean. N is the number of trials, as I indicated earlier. P is going to be the probability of success. In this case, we don't need to say P parentheses X or anything, because we only care about one probability, the probability of success. If we need to indicate the probability of failure, we can do so with a complement, 1 minus P. Lastly, X is going to be how many successes we want. For example, when I did the flipping a coin example, if I flip a coin 10 times and I want to see the likelihood of getting 7 heads. Well, N for that situation, N would be the 10 times I flip a coin. P would be the probability of getting a head, which is 0.5. 1 minus P, the probability of getting a tail, would also be 0.5. And the number of heads I'm looking for would be 7. So those would be all the values I would need. Again, we'll talk a little bit more about what this formula does in just a moment. Two more things, though, is that the mean and standard deviation of a binomial distribution, you can either do it in a complicated way that I'll show later, or the very simple way, which is using these two formulas. And these ones we would actually do by hand. The mean for or expected value for a binomial distribution would be solved by just doing n, the number of trials, times the probability of success. For example, with the previous example with flipping coins 10 times, I would have 10 flips, so 10 times the probability of getting a head, which is 0.5. 10 times 0.5 would be 5. So I would expect 5 heads out of 10. That's all that is. The standard deviation is a little bit more complicated, but still not enough that we can't do it in our calculator by just typing in some things. I would do the square root of n times p times 1 minus p. All of that under a square root. Both these formulas are also provided for you on the formula sheet for tests and quizzes and things, so make sure you know where they are. And because they are pretty easy to calculate, I highly recommend these ones you do by hand, or these ones you do using those formulas and not calculator functions. Okay. Now, before we dive into that formula, which I'll be talking about at the bottom of this page, we have a couple examples that we're going to look at and try to identify them as being binomial or not. I'll just say at the front that only one of these is binomial. If you want to pause the video now and check through A, B, C, or D and see if you can identify the one that is binomial, and also if you can point out why the other ones are not binomial, I'll give you a minute to do so. Okay, so if you did not already pause the video to try those, go ahead and do so. For the first one, it says an experimental drug is administered to 100 randomly selected individuals with the number of individuals responding favorably recorded. Okay, so far this sounds pretty good. It says overall that they're doing it for 100 individuals, so the number of trials is fixed. It seems to be binary because either they respond favorably or they don't, so it's one or the other. And the trials seem independent. One drug influencing somebody probably doesn't influence the likelihood of, or one person responding favorably probably doesn't influence somebody else responding favorably. So for bins, B-I-N, all of those seem to be satisfied. The one that I question is S. S is same probability. We don't know for sure what the probability of somebody responding favorably is, and we don't know if that's going to be the same from person to person. Therefore, I would say that this fails the fourth criteria for binary situations. This likely doesn't have the same probability for each. That one is a bit tricky. The next two, and actually the next three, should be a lot more straightforward. Surveying customers entering a sporting equipment store until a customer responds that he or she was shopping for a bicycle. Okay, well, let's go through. B, binary. They're either shopping for a bicycle or they're not, so that's good. I, independent. One person shopping for a bicycle probably does not influence somebody else shopping for a bicycle, so that's okay. Notice how I'm defending each of these. This is how you would write these down. N. Well, N is supposed to be a fixed number of trials. It says that they are doing this until a customer responds in a favorable way. That means they do not know how many trials they're going to do. Therefore, it fails the condition for n being fixed. So this is not binary. This is not a binomial situation. Thirdly, record the number of songs downloaded in a month for a group of 30 randomly selected college students. Okay, well, let's start at the beginning. Binary. It says that they're recording how many songs they download. That's not do they download or not. So the responses I could get are I downloaded 0 songs, I downloaded 10 songs, I downloaded 15 songs. Therefore, the responses are not binary in nature. It is not a binomial experiment. It fails the first condition. Lastly, observing that 10 of the next 20 customers at a grocery store checkout line use a credit card, given that the probability of using a credit card is 0.58. Okay, well, binary, they either use a credit card or they're not. That's all we're looking for, so B seems fine. For independent, one person using a credit card likely doesn't influence another person using a credit card, so that's likely okay. N is fixed because it says that they're doing 20 customers there. So 20 customers, so N is fixed. And lastly, the probability of success is the same. It is given to us as 0.58, and there's no indication that it changes. So D is the only one that satisfies all the conditions for binomial experiments. Okay. For a lot of questions moving forward, we are going to have to check things are binomial or not. All right, so this is what I had alluded to earlier. Back in Chapter 5, we looked at a probability of somebody liking sauerkraut. We knew that the probability of somebody liking sauerkraut was 0.21, and we were looking at, for the last situation there, what is the probability that of the first 4 people, 3 like sauerkraut and 1 does not? We had outlined the 4 different ways that can happen, where the first person likes it, and the other 3 don't. The second person likes it, and the other 3 don't. The third person likes it, and the other 3 don't. Or the last person likes it, and the other 3 don't. Those were all different situations that fall under the event of 3 liking it, and 1 does not. Actually, I guess these would be 1 person liking it, 3 do not. So I'll amend that right now. So just cross that off. This is 3 do not, and 1 does. That's what these probabilities are. So we have those highlighted here where the 1 person that likes sauerkraut can be in different positions. However, even though they're in different positions, we showed that no matter how you multiply it, it comes out to be the same answer in any way. So 0.21 times 0.79 times 0.79 times 0.79 gives you the same answer every time. However, what we needed to do was consider all 4 of those because they were technically 4 different outcomes that fall under the same event. We took all 4 of those, added them up, and we had a final answer of 0.414. Now, that took a lot of work. We had to consider all the 4 different situations, and we put them all down. So that took a lot of work. Alternatively, what we could do instead is use the binomial situation or binomial formula because this is binomial. They either like a sauerkraut or they don't, so that's B. 1 person liking sauerkraut means that another person doesn't. I think we also gave that they were considered independent. N was how many trials. We had 4 different people. And the probability of success of somebody liking sauerkraut was 0.21, so it was the same no matter how we did it. If we use the formula, scroll down here, the formula, which is given at the bottom yet again, is NCX, where N is the number of trials and X is how many successes. Well, we have 4 trials, and we want to see 1 person liking it, so that gives us 4 choose 1. The probability of success is 0.21, and we take that to the exponent of how many successes. Therefore, we have 0.21 to the 1 power. And lastly, 1 minus p is probability of failure, which is people not liking sauerkraut, which was 0.79, taken to an exponent of n minus x, where n is the number of trials minus x, which is number of failures, or number of successes. Therefore, n minus x will give you the number of failures, which is 3, 0.79 to the 3 power. That gives us our final answer of 0.414. That is how the binomial formula would work, where 0.21, 0.79 represents the probabilities for each, and that combination up front represents the number of different ways that the orders can be chosen. That's how you would do the binomial probability by hand, and that's how it works. And that's why we've technically have done it a couple times in the past. You can look back at your notes in Chapter 5, and you'll notice a few situations that would be binomial that we did solve by simply finding how many ways something can happen and multiplying by that. We also did a couple with marbles and bags, I believe. However, we're primarily going to do most of these with formulas in a calculator, and I'll get to both of these in a bit. But there are two different formulas, one called Binompdf and one called Binomcdf. Again, I'll get to both of these in just a moment. There's also some information here, including a table in terms of common phrases you tend to see. For example, at least and no less than and greater than or equal to all mean the exact same thing, which means greater than or equal to. We need to recognize these symbols because we will see these phrases in different ways, and we need to recognize what number of successes we're really looking for. Sometimes we'll look for an exact number of successes, sometimes we're looking for a direction. So we need to make sure we understand what these phrases mean. If you have trouble with them, make sure that you refer back to this table that's available to you. Lastly, before we go on into an example, we have another note. As the number of trials of n in a binomial experiment increases, the probability distribution of x becomes approximately bell-shaped. This should make you think of something else that we had in the past called the law of large numbers, which says that as you increase the number of trials in an experiment, you should approach either the probability or expected value for that situation. And the same thing kind of happens here, where as you do an experiment more and more and more, overall, the shape of the distribution that you create, if you notice, it may start off a little bit skewed, but as you do something more and more, it starts to become more and more bell-shaped. That's going to be a very important point for us because moving on from here, bell-shaped distributions are really nice to use. If you remember, even in the past, bell-shaped distributions are really nice because that allows us to use stuff like the mean and the standard deviation to describe it. Therefore, we can use things like the empirical rule and the mean and standard deviation. And also we have that we can use this as long as np1 minus p is greater than or equal to 10. Now, that's a weird condition that won't make a lot of sense right now, and we won't really use that much in this section. However, this np1 minus p greater than or equal to 10 will be an important condition moving forward. You will see this show up a lot in chapters 7 through 11. Well, specifically, actually, chapters 8 through 11. So, though this is not important right now, keep this in the back of your head. All right, let's finally go through some examples so you can do some of this in action. We have 3 pages of examples here to help you through this because binomials can be a little bit complicated. Okay. So we have here, a quiz has 5 multiple choice questions, each of which have the possibilities A, B, C, or D. That means that the probability of getting a question right is 1 out of 4 because it's A, B, C, or D, or 0.25. You're going to guess on all 5 questions, which is not the best. We've actually done an example before showing that. And we're going to construct the binomial probability distribution. However, before we do that, what we're going to do is first explain why this is a binomial probability experiment. So we're going to do so with the 4 conditions in bins. Remember, do not just write down the word bins and call it a day. For B, we want to confirm that it's binary. Well, for each question, you either get it correct or incorrect. Whoop. Sorry. B. For each question, you get it right or wrong, or correct or incorrect. So that satisfies the conditions for B, for it being binary in nature. I stands for independent. So getting one question correct does not influence the chance of getting another correct or incorrect. So either way. So they are independent of each other. N is supposed to be that n is fixed, and in this case we have that n equals 5. That's enough for us. That's indicating what the sample size is, or the number of trials. That's all we need to know. And S, we need to indicate that the probability is the same. We have the probability of getting a question right is 0.25 for each question. So it's the same for each of them. Those are our 4 conditions for bins, and that's all we need to point out. So that's everything. All right, now that we know it's binomial, now we can fill out this probability distribution. So that's what we're going to do in part B, compute the probability distribution, or complete it. And that's what we're going to do here. We're just going to fill out for each value what the probability is. Now I'm going to talk about those 2 programs you have available and where they are. The 2 programs you have, I'm going to go back to the main screen, so I'm going to go second, quit, so I'm back here. The 2 programs we have are Binomial Pdf and Binomial Cdf. Those are both located in the distribution section, which is where we're going to be for a lot of the chapters moving forward. To get to there, if you see above the button VARS, which is diagonal from the bottom arrow, you see DISTR in blue on my calculator. It may be yellow on your calculator depending on the calculator style. To access that, we need to hit second, VARS. We see stuff like normal PDF, normal CDF. What we want are the ones that start off with binom, and those don't show up for a while. You need to scroll down until I think you get down to A and B, and you see Binompdf and Binomcdf. Now we will use both of these, but they have different uses. Binompdf is used to find an exact number of successes. So I'll even write that here. Binompdf is for an exact number of successes. Whereas Binomcdf, CDF stands for cumulative distribution, whereas P just stands for probability. C stands for cumulative, so this is a cumulative number of successes. Explicitly, it's from 0 up to x. So from 0 successes up to however many successes we indicate. That is sometimes useful if we need to add a lot of probabilities together. Binomcdf can help us skip a couple steps. However, in this case, when we're building the probability distribution, we want the probability for each of them, so we're just going to do Binompdf. So that's what I'm going to do over here. So Binompdf. When you open Binompdf, you probably have the wizard. If you do not have the wizard, you're going to follow the same 3 prompts, but just put commas in the middle. So first, you're going to follow with first put the number of trials. In this case, we have 5 questions, so we have 5 trials. The probability of success for each, which is P, is 0.25. And the X value is going to be how many successes we want. Well, I want to fill out the first column, or the first row rather, which is 0 successes. So I want 0. And I'm going to paste that. If you do not have the wizard, it should look like this. 5, comma 0.25, comma 0, and then you end the parentheses. Hit enter to run that, and what you get is 0.237. That would be the probability of getting 0 successes, or getting 0 questions correct. I can run that again and do second VARS. Binompdf is on A. My calculator is kind of slow, so I'm just going to skip down to that. And we have 5 trials, 0.25 probability of success, and 1 success now. So I only need to change that last number. That will give me a probability of 0.396. Okay, now if you notice, this can get kind of tedious, particularly if you're building a distribution with a lot of numbers. This isn't too bad because it's not that many, but you can do this all at once, which is why I asked you at the beginning of this video to have the numbers 0 through 5 in your calculator in list 1. There is a way of optimizing and doing this all at once. In order to do that, like we have for list manipulation in the past, we're going to go over to list 2, and we're going to highlight the top of it. So this so far should sound familiar for our list manipulations that we've done before. Once I have the entire list highlighted, what I want to do is go get my Binomial Pdf function. So while I have L2 highlighted, I'm going to do second vars, and I'm going to go get Binompdf, which again is on A. When I have Binomial Pdf, I need to remember that there are still 5 trials. The probability of success is 0.25, but the number of successes I want is in that list of L1. So instead of putting a specific number here for X, I'm going to put in second 1 to get L1. Then I paste that, and you should see that now in L2. It should say L2 equals maybe ... f5, 0.25, L1. If you do not have the wizard, that's how you would type that in. So you would get Binomial Pdf, which would paste, then the parentheses would probably already be there, and you do 5, 0.25, L1. Hit enter, and you should have the probabilities populate list 2. So we get for 2 successes, we get 0.263. For 3 successes, we get 0.088. For 4 successes, we get 0.01 or 0.015. And for 5 successes, we get 9.8 e negative 4, which is in scientific notation. If you need to see more of these instead of just what's on the list, you can always scroll down through them, and you should see the full decimals listed out at the bottom of the screen. All right, so that's how I would typically do binomial distributions. That's a much faster way of doing it, and you get to see all the probabilities. Okay, so if we need to find individual probabilities, that's what we can use that for. We could just use Binomial Pdf to find an individual probability. However, if we need to find multiple probabilities, we may need to add things together. For example, on C, it says, what is the probability that a student guesses on all 5 and gets fewer than 3 correct? So less than 3. Less than 3, in terms of number of successes, numbers that are less than 3 would be 0 questions correct, 1 question correct, or 2 questions correct. 3 is not less than 3, so we would not consider 3, 4, or 5. In order to solve this, what I could do is add up those 3 values of 0.237 plus 0.396 plus 0.263. I can add all those together, and that can give me my probability of getting less than 3 questions right out of 5. So we can do that over here. So we'll do 0.237 plus 0.396 plus 0.263, and we get 0.896. Now there's another way we could do that, and that's using the other binom function, Binomcdf. Remember, as I said above, Binomcdf adds probabilities from 0 up to a number of successes. And that's what we want to do here. We want to add up the probabilities from 0 up to 2 successes, inclusive. So I'm going to go get Binomcdf, second vars. Binomcdf is on B. And then for Binomcdf, it'll have the same 3 inputs: trials, probability, and number of successes, or NPX. The number of trials is still 5. Probability of success of 0.25. And in this case, the number of successes I want is the maximum number of successes I care about. In this case, I want less than 3, which means 2 or less. So I'm going to put an x value of 2. So we'll have 5, 0.25, 2. is how I would show your work if you did it like this. And that gives us, should be the same answer as before. We get about 0.896. So same answer. Notice Binomcdf can save us a bit of time because we would not have needed to calculate Binompdf for each of 0, 1, 2, and 3 and then add them. We can sometimes just do Binomcdf to add them all together. However, keep in mind the limitation of Binomcdf that it only adds up the probabilities from 0 up to something. So if we want some other range, we have to be a little bit more creative. Interpreting this, we are going to put it in terms of 100, like we did with probabilities in Chapter 5. So we're going to say, if we did this 100 times, or in 100 repetitions, we would expect fewer than 3 questions, which is what our event was. So fewer than 3 questions would be expected to be correct. In this case, looking at my probability, 0.896 is roughly 90%. So we'd expect fewer than 3 questions to be correct in about 90 of those trials. All right, let's do another one. What is the probability that a student guesses on all 5 questions and gets at least 4 correct? All right, so at least 4. At least 4 means greater than or equal to 4. So in order to do that, if I look at my table here, at least 4 means 4 or 5. So what I can do to do that is to add those two values together and have 0.015 plus 9.8 e negative 4 would be 0.00098. So that would give me about 0.001598 if I were to add those together. Or alternatively, we could use Binomcdf, but by applying complements. Remember, Binomcdf adds up the probabilities from 0 up to the number of successes, which is the exact opposite of what we want. What we don't want is 0 through 3. So what I could find instead is take Binomcdf of 5 trials, 0.25 probability of success, and 3 successes. I'll find all of those probabilities together, and if I take that away from the total of 1, that should give me the exact same answer, or approximately the same because I rounded off the previous one. So let's do that. Let's do 1 minus, and then I'll go get Binomcdf of 5, 0.25, and 3. That gives me 0.15625. The reason why it's a bit off is because, again, there was some round off error there. So that's why it's a little bit different. But about the same. All right. Now, in this case, we would say in 100 repetitions of this experiment, at least 4 questions would be expected to be correct, which is what we were caring about. And in this case, my percentage is less than 1%. I'd expect at least 4 questions to be correct 0 times, because this is roughly 0.1%. So of the 100 trials, I wouldn't really even expect this to happen once. And lastly, we can find the mean and standard deviation. Now, the mean and standard deviation, we have the formulas for, and the formulas are nice and easy. Formula is NP, and for standard deviation, it's NP1 minus P. If you do NP here, that's 5 times the probability of success of 0.25, and 5 times 0.25 gives you 1.25. For the standard deviation, that gives you the square root of 5 times 0.25 times the complement, which is 0.75. If you do that, that gives you the square root of 5 times 0.25 times 0.75, or times 1 minus 0.25. and that gives you 0.968. Now that would be the easy way to find these two. I said before that there is a complicated way, and that's by using the list that we did. The complicated way would be to create these two lists of values and probabilities, and then running one-var stats on those. If we do that, we should get the exact same answers. So I'm going to run one-var stats on list 1 and the probability list in list 2 as my frequency list. If I hit calculate, I get a mean of 1.25 and a standard deviation of 0.968. The exact same answers. So that's another way that you can do it. If you already have the list made, you can do one-var stats. However, if you do not do that, which takes some extra time, you can simply do NP and the square root of NP1 minus P. All right. So that's one example of binomial. Let's do a couple more because, again, I know that these are a little bit tricky. So we have page 8 and page 9 here. According to an airline, flights on a certain route are on time 75% of the time. Suppose 10 flights are randomly selected and the number of on-time flights are recorded. So again, we're going to explain why this is a binomial experiment. So for B, it is binomial because they are on time or not on time. That's all I need to know for B. That means it's binary in nature. I, one flight probably doesn't influence another. We don't know that for sure, but we can hopefully assume that. We can safely assume that they don't. N is the number of trials, and it has to be fixed. In this case, we have that N is 10. It is given to us that there are 10 flights. And S is that the probability is the same, and we have that the probability equals 0.75 and is not implied to change. And that's it. That explains why it's a binomial experiment. Note that I didn't need to go too in-depth with each of these. However, you do need to explain them. Do not just write down the word bins. That is not enough as an explanation, and most of the time we do not count that at all as credit. So do not just write the word bins. Make sure you can explain it. So here we have N is 10 flights. The probability of success is 0.75. We're going to be using that for the next few questions. Find and interpret the probability that exactly 6 flights are on time. Okay, well, exactly 6, since we're doing an exact probability, that means we can solve this by doing Binomial Pdf. Remember, Binomial Pdf is for an exact number of successes. For Binomial Pdf, we're going to put in the number of trials as 10. The probability of success is 0.75. And the number of successes we want is 6. So second vars, Binomial Pdf, and we put in those values. 10, 0.75, and 6. 0.75. Okay. I think this is an answer of 0.146. And that's it. This is far more convenient than how we would have had to do it before, because we would have had to consider putting 10 things in order and how many different ways we can have 6 of those flights being on time and the other 4 not, which there's a lot. There would be 10 choose 6. There's a lot of different ways you could do this. Next one, find and interpret the probability that fewer than 6 flights are on time. Okay, fewer than 6 is less than 6, which is the same thing as less than or equal to 5. Since we're doing a combination of a bunch of probabilities, we would like the probability of 0, 1, 2, 3, 4, or 5 flights being on time. We're going to do a cumulative probability up to 5 successes. That will add up all the probabilities from 0 up to 5. Otherwise, you would have to do Binomial Pdf for 0, Binomial Pdf for 1, Binomial Pdf for 2, 3, 4, and also 5, and then add them all together. All right, so we have 10 trials, 0.75 probability of success, and 5 successes at most. That's what less than 6 means. That will give us an answer of 0.078. Next, find and interpret the probability that at least 6 flights are on time. Okay, well, at least 6 means greater than or equal to 6. Well, at least 6 would be 6, 7, 8, 9, or 10, right? That doesn't work too well directly with Binomcdf, because Binomcdf wants 0 up to something. However, what it does work well with is the complement of what we just solved. This is less than 5, or less than or equal to 5, so 0, 1, 2, 3, 4, or 5. If we take that away from 1, what we get is the probability of everything else. So we can do 1 minus Binomcdf of 10, 0.75, and 5, and that would leave us with the probability of 6, 7, 8, 9, or 10. So we can solve this by doing 1 minus that previous answer of 0.078, and we get 0.922. Lastly, or we have 2 more, sorry. Find and interpret the probability that between 4 and 6 flights inclusive are on time. So between 4 and 6 flights inclusive, that means 4, 5, or 6. There's a couple ways to do this, and I don't really think that either of them are better than the other. It's really up to you. To do 4, 5, or 6, what you could do is, I'll just do B for binom. You could do Binompdf of 10, 0.75, and 4. And then you could add that to Binompdf of 10, 0.75, and 5, and do the same thing with 6. So plus Binompdf, again, I'm just using bpdf for shorthand so I can save room, 10, 0.75, and 6. That would add all 3 of them together. Or, there's another way to do this, although this one's a lot sneakier. What you could do is consider that if you do Binompdf or Binomcdf up to 6, you would have 0, 1, 2, 3, 4, 5, and 6. This is what Binomcdf would do. So if I did Binomcdf up to 6, I would add all these probabilities together. But I don't want all of these. I want to take out 0, 1, 2, and 3. Well, I can do that by subtracting Binomcdf up to 3. That would take out these values here, and all I would have left is the probability of 4, 5, and 6. Either of these would solve in the same way, and again, I think the second one takes a little bit more thinking, so therefore I don't really see either of them as better than the other. It's really up to you. I like the second one myself. I think it's a little bit more elegant, and so I'm going to solve with that one. But if you want to solve with the first situation and make sure you get the same answer, you should get the exact same answer. So I'm going to use with Binomcdf 10, 0.75, and 6. And then before hitting enter, I'm going to hit minus and go get Binomcdf again. And then take away the values up to 3. That will give me an answer. Either way you do it, that will give me a final answer of 0.221. Either direction will solve for the same thing. Lastly, would it be unusual for 10 flights to be on time? Notice that word again, unusual. Unusual, remember that we need to check to see if something is less than 5% chance. That's what it means to be unusual. So let's check the probability of all 10 flights being on time. That means that we're doing Binomial Pdf, because we're looking for exactly 10 flights being on time, not at least 10. So if we're looking for exactly 10, that's going to be 10 trials, probability of success of 0.75, and 10 successes. If we solve for that, we have second vars. Binomial Pdf is on A. We have 10 trials, 0.75, and 10. Remember, if you don't have the wizard, it would be 10, comma 0.75, comma 10, like I wrote down there. And you get an answer of 0.056. Now, this is really close, but it is greater than 0.05. Therefore, no, it is not unusual. It's really close, but it needs to be strictly less than 5% to be considered unusual. All right, hopefully you're getting the hang of it, and hopefully you're seeing how quick these questions can be solved. Just understanding which formula you use based on the wording here, and plugging in appropriately. All right, let's do one more that has 3 parts to it. According to a study, the probability a randomly selected individual will not cover his or her nose when sneezing is 0.267. So that's the probability that they will not cover their nose. So we have P equals 0.267. I always like to write down numbers outside of the description. Suppose you sit on a bench in a mall and observe people's habits as they sneeze. What is the probability that among 10 randomly selected individuals, so n is 10, exactly 4 do not cover their nose? Notice that the word we have here is exactly. So that means we're doing Binomial Pdf. In that case, it's Binomial Pdf. Here we have 10 trials. Probability of success, which is not covering their mouth, is 0.267. And then we have exactly 4. So that will give us second vars 10.267, 4 into Binomial Pdf. Make sure you use PDF. And that gives us a probability of 0.166 approximately. All right, if you haven't already, pause the video and see if you could solve the last 2 without me. And then unpause and see how you did. All right, what is the probability that among 10 randomly observed individuals, so n is still 10, fewer than 3 do not cover their nose? So fewer than 3 means less than 3, otherwise known as less than or equal to 2. Since we're doing something like this, that means Binomcdf is better. We can just do one function of Binomcdf to solve this instead of 3 functions of Binompdf. 10.267 and 2, since we want at most 2 successes. So we have second vars. And then for Binomcdf, we have 10 trials, 0.267 chance of success, which is not covering their nose. And then 2 successes at most. That gives us an answer of 0.475. Lastly, would you be surprised if after observing 10 individuals, fewer than half covered their nose when sneezing? Okay, so fewer than half covered their nose. So fewer than half means less than 5, which means less than or equal to 4. Now you could do this with the probability that we had, but we had the probability of success was 0.267, and that was them not covering their mouth. But we want them covering their nose. So that means we want to actually work with 1 minus p, which is 0.733. Therefore, we want to use Binomcdf, this one's a bit tricky. Binomcdf of 10 trials. The probability of success in this case is covering their nose, and probability of them covering their nose is 0.733. And we want at most 4. That would be fewer than half. So we can do second vars, and we have 10.733 and 4. That gives us an answer of 0.027. A very unlikely chance. Now you could do this another way if you wanted to use 0.267. Fewer than half covering their nose would mean that less than or equal to 4 cover their nose, which means that 6 or more did not cover their nose. 6 or more could also be taken by doing 1 minus Binomcdf of 10.267 and 5. That would find the probability of 6 or more covering or not covering their nose. So we can do 1 minus for Binomcdf, 10.267 and 5. And we should get the same answer. There we go, 0.027. So that also gives the same answer. There's a couple ways to solve that one. I think the top one's a little bit easier. It doesn't involve doing a complement for the whole binomials function. All right, that does it for Chapter 6.2 and all of Chapter 6 in general. With that said, you should be able to go through and complete all the homework for Chapter 6 at this point, which I recommend doing before diving into Chapter 7. You also probably have a test before that anyway. If you have any questions, feel free to put those into the comments below or ask your instructor directly. But with that said, I hope you have a wonderful day.